Let's look at some examples of calculating inverse Z transforms. And we'll do this actually using partial fraction expansion and then our table of transforms. So as an example, let's consider the partial fraction of expansion of this particular Z transform, Z squared. I'll have two simple poles that Z equal 1 and Z equal 2. Corresponding partial fraction expansion here, notice the order of the numerator is the same as the denominator, so it's not in proper form. So I have to determine the constant term. But the partial fraction expansion is given by this expression. And then now, using my table of transforms, we know that the inverse Z transform of 1 is our discrete time impulse. And then these two terms can both be found in row 7, or pair number 7 in our transform table. This term transforms as u of n minus 1. And the second term transforms as, because of the 2 in the denominator, I'll have 2 to the n minus 1, u of n minus 1. I can simplify this a little bit. It's delta n plus, writing 4 as 2 squared, 2 to the, and I'll have 2 squared times 2 to the n minus 1 will give me n plus 1, and then the minus 1 all times u of n minus 1. And if I evaluate this for a couple different values of n, you can see that x of 0 is just 1 due to the impulse. This part hasn't kicked in yet. And then x of 1 I get by evaluating this part. The delta of 1 is 0. And so this is 3. X of 2 is 7. X of 3 is 15, and then so on and so forth. Okay. Now, there's actually a little trick that we can play to get a simpler form, and it actually makes finding our inverse Z transforms quite a bit simpler. If you note that the transforms, the Z transforms in our table, most of them have a Z in the numerator. So we can usually end up with a simpler expression for x of n by first finding the partial fraction of x of z over z. So in this case, x of z over z is z over z minus 1 times z minus 2. And notice this is already in proper form. It's going to have a different Z transform. This will actually be the Z transform of this expression is minus 1 over Z minus 1 plus 2 over Z minus 2. Okay. Now, and I don't want the inverse transform of x of z over z. I want the inverse transform of x of z. So now, after doing the partial fraction expansion on x of z over z, I'm going to multiply both sides by z to get an expansion where I have z terms in the numerator. So I can find both of these now in my table of transforms, and the result is x of n is just, the first term is just our unit step, and then the second term is actually plus 2 times 2 to the n times our unit step. And I can rewrite this just as 2 to the n plus 1, writing 2 as 2 to the 1, and then combining the exponents here, minus 1 times u of n. Okay. Now this looks a little different than the sequence we found on the previous page. They are identical, and you can verify that just by evaluating this at a few different values of n. We see that x of 0 is 1, x of 1 is 3, x of 2 is 7, and so on and so forth, just as we had before. So this is a slightly simpler form. You could show these are equal algebraically. The two different sequences we have for x of n are identical, but this is a slightly different form. And again, this technique usually makes the process of finding the inverse Z transform a little simpler. So the steps here are, so the recommended steps is do a partial fraction expansion of not x of z, okay, not the transform that you're really interested in, but actually that transform over z. Do a partial fraction expansion, multiply both sides of the partial fraction expansion by z, defined an expansion for x of z, and then the third step is look up the inverse transforms. So again, this is the recommended procedure for finding an inverse Z transform.